Hello all. Today we are going to study about asymptotic notations. When we talk about algorithms, then to solve a given problem, several algorithms may exist. Out of all the available options, we have to choose the one which is efficient both in terms of time as well as space with respect to the input given to the algorithm. Now, the question is why to pick an efficient solution? So, the answer is because when we talk about computers, then they are fast, but not infinitely fast. Similarly, memory, yes, it is inexpensive, but it is not free. So, the algorithm which makes use of these resources, that is, time and space, wisely should be selected. Also, differences in algorithms based on time and space are more significant as compared to the hardware or software being used for implementation. Overall, the algorithm whose running time increases slowly with an increase in input size has to be selected. That is, the one with lowest rate of growth of the running time should be selected. Here, by input size, we mean larger values of input sizes possible, not the very small ones. We will take a very simple example before moving further. So let's say we have to write an algorithm such that in an array, an element at index I will have sum of all the elements from index position 0 to I. One can have many options to do this task. Say in the first option, we are using this solution where we are computing sum of elements from index position 0 to I every time by means of a for loop at line 3. On the other hand, the same objective can be obtained via a simple addition of consecutive elements of an array from left to right, as it is shown in option 2 here. Out of these two, one can easily say that option 2 is better. Talking in terms of order of growth, then option 1, it has two nested for loops, so its order is n square. On the other hand, for option 2, the growth is linear. Out of all the resources required by an algorithm, in this course, we are going to talk about computational time. We assume that an algorithm is implemented using a single processor RAM model of computation without any concurrency. The basic operations that can be executed in such a machine are data movement operations like load, store, copy. There will be control instructions including branching, both conditional, unconditional, subroutine call, and return. Lastly, there will be all arithmetic and logical operations. After writing an algorithm, we have to identify all such primitive operations which are independent of any programming language. They can easily be identified once the algorithm is framed properly. For example, if we look at the algorithms we have just proposed, then for option 1, we have written 5 lines, and these are those 5 lines. Let the execution cost associated with each of these lines of a RAM model be C1, C2, C3, C4 and C5. Next, we have to look at the number of times each of these lines is being executed. That means we are talking about frequency. So, the line 1 gets executed for n-1 times when the condition results in true, and it will get executed one more time when condition gets false. So, total frequency of line 1 is n. Line 2 and line 5 get executed only if the for condition at line 1 returns true. Thus, their frequency is n minus 1. The inner for loop at line 3 is dependent on the outer for loop variable I. For each value of I, the inner for loop executes I plus 1 times. Like when I equals to 1, J loop gets executed for J equals to 0 and J equals to 1. Then for I equals to 2, J loop will give true for J equals to 0, J equals to 1 and J equals to 2 and so on. In addition, there will be one more execution of this inner J loop at line 3 which leads to false. Thus, for each value of I, that is I equals to 1 to n minus 1, the inner for loop gets executed for I plus 2 times. Lastly, line 4 gets executed only when the loop condition at line 3 gives true. Accordingly, it will get executed I plus 1 times for each value of I, where I is varying from 1 to n minus 1 again. Now, to get the order of growth, we have to multiply corresponding costs and frequencies and add all the terms together. Here, we will get this equation. The summation of I from I equals to 1 to n minus 1 leads to an arithmetic progression series of n minus 1 numbers. Hence, both the summations lead to n into n minus 1 divided by 2 value. And the constants in both the summations, that is 2 and 1, will get add up n minus 1 times. So, after solving these two summations, we will get this equation. And finally, rearranging the terms based on the powers of n, we will get this last equation. Here, the highest power of the input variable n is 2. Therefore, rate of growth is quadratic for this algorithm. On the other hand, the algorithm which we have considered as option 2 has a linear rate of growth with respect to the input variable n. As we can see here, the for loop at line 1 gets executed n times, where n minus 1 time is for the true condition of the loop and plus 1 for false condition of the loop, and line 2 gets executed only for the true condition of the loop at line 1. Thus, its frequency comes out to be n minus 1. Hence, the order comes out to be linear here. Thus, this algorithm is better than the previous one. Actually, the running times of algorithms are expressed using asymptotic notations as a function of the size of algorithms input. Also, the commonly associated running times during algorithm analysis is the worst case running time, the average case running time, and the best case running time. Out of all these, we are interested more in the worst case running time analysis of an algorithm. To better differentiate among these three running times, let's take the insertion sort example. Insertion sort is an efficient algorithm to sort a short sequence of numbers. Let's look at the working of insertion sort now. Then we will look at the algorithm and its analysis so as to understand the worst, best and average running times. Here is the sequence which is to be sorted using insertion sort. The idea is the left half of array is sorted and the new element is to be inserted into it at the correct position. We will start with single element and increase the size by 1 in each iteration. Single element is always sorted. So we start with the second element. Here we have 6 in the sorted list and element 3 has to be inserted at its correct position. We store 3 somewhere and compare 6 with 3. As 6 is greater than 3, so 6 will be shifted ahead by 1 position. Since there is no other element, so 3 is placed at the first place now. So we have 2 elements in the sorted sequence, as you can see here with the green boxes. Next, we have to insert 9. So insertion of 9 will not change the position of any element in the sorted sequence as 9 is greater than 6. So there will be 3 elements in the sorted list now. Next, insertion of 1 takes place since 1 is less than all the other elements, that is 3, 6 and 9. So they all will be shifted one by one. First 9 will be shifted, then 6 and then 3. After this we have reached at index 0. So we have to stop and place 1 at the first index position of the array. So there are 4 elements sorted now and they are present in the left side of the array, as you can see here. Lastly, insertion of 8 will shift only a single element 9 as rest all the elements are less than 8. After this shift, 8 will be inserted at its correct position. With this, we have completed the sorting of the given sequence. An algorithm to implement the same is written here. Input will be an array A having n elements and output will be a sorted array in increasing order. The steps to be followed are also shown. Next, we have to start with the analysis. Let the execution cost associated with each of the 7 statements be C1, C2, C3, so on up till C7. Now, line 1 gets executed n times, n minus 1 for true condition and plus 1 for the false condition. Line 2, line 3 and line 7 get executed for each execution of the for loop at line 1 whenever it gives true. So their frequency is n minus 1. Now the while loop at line 4 is responsible to shift the elements by one position so that the new element gets inserted at the correct position. The number of times this loop iterates depends on the input sequence. So for now, we assume that for each value of I, line 4 is executing Ti times with I varying from 1 to n minus 1. Line 5 and line 6 get executed only when condition of while loop evaluates to true. Thus, they will get executed one lesser than Ti for each I varying from 1 to n minus 1. Now, the final equation after multiplying respective cost and frequency values followed by addition is as shown here. The best case of insertion sort occurs when the array is already sorted. In this case, the while loop condition at line number 4 always evaluates to false. Thus, line 5 and line 6 will never get executed. Therefore, the best case running time is as given by these equations. Overall, it comes out to be a linear function of n. On the other hand, the worst case happens when the array is in reverse sorted order, that is the decreasing order, as we are trying to arrange the elements in increasing order. Then in each iteration, all the elements forming the sorted list in the left half of the array has to be shifted by one position. So line 4 gets executed for 2, 3, 4 and so on up till n times, which is nothing but a sum of n natural numbers except 1. Accordingly, we will have n into n plus 1 by 2 minus 1 in place of summation for C4. Similarly, for C5 and C6 summation, we will get an arithmetic series of first n minus 1 natural numbers. Therefore, we will have n into n minus 1 by 2 at 2 places. Also, the resulting function in this case will be a quadratic function, as it is shown with a power of 2 for the input variable n. Talking about an average case, that means while loop gets executed for I by 2 times for each value of I, which again comes out to be a quadratic function. The analysis of algorithms is simplified by following some abstractions. That is, we will consider only the leading term and discard others. Also, all the coefficients of the leading term will be ignored. So, here in best case, we get only n, and in the worst case, we will get only n square as order of growth. In other words, we can say that we are working with asymptotic efficiency of algorithm, where the concern is how the running time of an algorithm increases with the size of the input in the limit. In this course, we will discuss asymptotic notations which are well suited for characterizing the running times. The first is big O notation. It gives an asymptotic upper bound only within a constant factor. If Fn is the function representing time taken by an algorithm, then by writing Fn equals to big O of Gn, we mean that for some positive constants C and N naught, value of Fn will always be less than C times of G of N for all N greater than equals to N naught. The same is shown with the help of this graph here. It gives the worst case running time of an algorithm in short. Next is big omega. It is used for best case running time of an algorithm as it gives an asymptotic lower bound for a function. Fn equals to big omega of Gn means there exists positive constant C and N naught such that the value of Fn is always greater than C times G of N for all N greater than equals to N naught. The graph is depicting the same here as well. Lastly, there is a theta notation that will give both an upper and lower bound. That is, it gives an asymptotic tight bound by writing Fn equals to theta of Gn. We mean there exist positive constants C1, C2 and N naught such that the value of Fn lie in between C1 times of Gn and C2 times of Gn for all n greater than equals to N naught. So basically it is providing a bound of a function Fn from both the ends, that is lower as well as upper. Let's take an example to compute all the three bounds now. So we have a function Fn as n square by 2 minus 3 times of n, and we have to show that it has an asymptotic upper bound of n square. That is, we have to prove Fn equals to big O of n square. To show this, we have to compute constant C1 and n naught such that n square by 2 minus 3n is less than equals to C1 times of n square for all n greater than equals to n naught. After dividing the equation by n square, we get half minus 3 by n less than equals to C1. Now we have to check for various values of n starting from n equals to 1. In this example, any positive value of c greater than equals to half will work as we are subtracting from 1 by 2, and with increasing value of n, 3 by n will only be reduced. So the given inequality holds for any n greater than equals to 1 and C1 greater than equals to 1 by 2. There can be many possible solutions. One can be n naught equals to 1 and C1 equals to 1 by 2. Similarly, to obtain asymptotic lower bound, that is big omega, we have to compute constant C1 and N0 such that C1 times N square is less than equals to N square by 2 minus 3N for all N greater than equals to N0. Again, after dividing by N square, we obtain C1 less than equals to 1 by 2 minus 3 by N. Next, we have to check for various values of N starting from 1 to get the exact value. Here, we will obtain a negative value of a constant for N equals to 1 to N equals to 5. At N equals to 6, possible value of C1 is 0. Thus, it does not hold again. Then at N equals to 7, C1 comes out to be less than equals to 1 by 14. So again, many possible solutions are there. One can be N0 equals to 7 and C1 equals to 1 by 14. Lastly, the theta bound can be obtained by combining the results for big omega and big O. For big O, any value of n greater than equals to 1 and constant greater than equals to 1 by 2 will work. Similarly, for big omega, n has to be greater than or equals to 7 and constant should be less than equals to 1 by 14. Based on these two, we can write for C1 equals to 1 by 14, C2 equals to 1 by 2 and N0 equals to 7, the function n square by 2 minus 3n is bounded asymptotically by theta of n square. In this way, one can compute the three asymptotic bounds along with the constants and n naught for any given function. In this course, we will work with a few such examples during starting. Then later, we will focus solely on asymptotic bounds without worrying much about the constants and n naught. We will see two more notations now. First one is small o, upper bound obtained with big O notation may or may not be asymptotically tight. Like if we say Fn equals to 2 times of n square, then we can say that Fn equals to big O of n square. And yes, it is asymptotically tight. On the other hand, if Fn equals to 2 times of n, then also we can say Fn equals to big O of n square. But this time it is not asymptotically tight. And to denote such asymptotic upper bounds which are not tight, little o notation can be used. And by writing Fn equals to little o of Gn, we mean for any positive constant c greater than 0, there exists a constant n naught greater than 0 such that 0 is less than equals to f of n is less than c times of Gn for all n greater than equals to n naught. Thus, if Fn equals to 2 times of n, then writing Fn equals to big O of n square is incorrect. Though we can write Fn equals to little o of n square. Similarly, if Fn equals to 2 times of n square, then we cannot write Fn equals to little o of n square, as this bound is tight. So little o cannot be used. We have to use big O. Also note here that we are saying for any constant, that is, the definition is not restricted to a few constants. Instead, the constant could be any in case of little o, which is not the case with big O. There we were talking about the set of constants which are valid. In a similar way, if we have an asymptotic lower bound which are not tight, then instead of big omega, we have little omega. So by writing Fn equals to little omega of Gn, we mean for any positive constant C greater than 0, there exists a constant n naught greater than 0 such that 0 is less than equals to C times of Gn less than f of n for all n greater than equals to n naught. For an example, if Fn equals to n square by 2, then we can write Fn equals to little omega of n. But writing Fn equals to little omega of n square will not be true. So today we have discussed notations that are popularly used to get rate of growth of a function, and this growth can be logarithmic, exponential, polynomial, or any function of an input size. Like here we have shown a few functions, namely log n, root n, n, n log n, and 2 to the power of n. As one can observe that the least growing function is log n and the fastest growing function is 2 to the power of n. So the algorithm with log n growth is the best to choose among the given 5 options. So in this way, one can decide which algorithm to pick among the available ones. That's it for today. Thank you.